Hello and welcome back everyone to Kanai Lab. This is going to be the second and last video on the series of AI-powered pneumonia detection. In our previous video, we deployed a deep learning model using Flask API. But how did we build this model? In this video, we will walk through the step-by-step process of developing a pneumonia detection model using transfer learning technique. Specifically a CNN variant of VGG16. Have you ever heard about of transfer learning? The transfer learning is a machine learning technique where a pre-trained model, which is already trained on a massive data set like ImageNet, which can be reused for different but related tasks. Do you want to see what is ImageNet? This is going to be the ImageNet, which has trained on total number of images. So we can see 14197,122. Huge data set like our WordNet, like a Wikipedia, but instead of word, here we have images. So this is already trained on the image data set, which can be reused for our related task. In our case, the related task is identify whether the image represents a normal image or a pneumonia images. So this is how we leverage existing feature of extraction capability, which can save time and computational resources. So why do we need transfer learning then? The model has already trained to detect the general features like adjacent features. And also it could be helping you to get saving time, faster training, and better accuracy. You can see from this picture, from the ImageNet, the task one is already completed, and we are acquiring the transfer from the base model, which is from this base model of ImageNet data, and we are taking the task of detecting my new data as data number 2, which can be from chest X-ray, and we will be taking the knowledge from the model 1. Still, we are taking the model 1, but you can see the requirement on the following is difficult based upon the chest X-ray. That's something called transferring the knowledge. So before we diving into the code, let us understand and what are the libraries we need. So the library we are going to use it as usual. We are running this particular program by using TensorFlow and Keras. So let us execute this. So what are we going to use it? We are going to use it very simple. Our libraries like NumPy. We all know what is NumPy. NumPy is for numerical computation. And we are going to take Matplotlib. We have some visuals which is representing how the X-rays of normal and the second one, the pneumonia is different. And also we will be taking the advantage of TensorFlow and which will be using for a framework for numerical and tensor based calculation. We will be using the pre-processing and also we will be taking the model, deep learning model or sequential model. And also, as I mentioned, this is going to be a transfer learning technique, which is 16, we are going to use it. And all the layers of TensorFlow Keras model like contouring, max pooling, flattening the layer and the dense layer. And if you have any dropout or something called kind of an overfitting, we will be using this concept of overfitting in the dropout and we will be having a batch normalization. And also we will be having something called ADAM, which is nothing but a optimizer to run the model. This is nothing but the library, the minimum requirement for our required process. So with that, we will be moving to our data set. So instead of taking here, I wanted you to take our data from the folder. You can see the chest X-rays here. So we have three different types of data. What are the different types of data? The major important thing is nothing but our train data. Have you heard about train data? The train data is always for machine learning or deep learning. Nothing but we are going to train our model with the train data. So why do we need test data then? We need the test data only for one purpose, evaluation. What do you mean by evaluation? It is nothing but whether it is working good or bad. Very simple. And also we will be having some data. I'm giving a name, some fancy name, challenge. This is nothing but validating with the new images because we already trained the model and we tested the model, but we wanted to ensure whether it is working good or bad using a new data. That's called challenging data. That's how some people say that validation. So we will be using a name of challenging the data. So I hope this is again clear. We will be back to our module and we will be back to our Jupyter notebook. Here we our code, and this code is already identified what is the library required. As I mentioned, my data is available on the chest X-ray, which is chest X-ray. We have trained data and we have test data and we have challenging data, all the data, and we are calling one by one data. And I just wanted to understand what is the number of counts in each and every folder, how many trained, how many tests, how many challenging data. And I just wanted to understand the numbers. I can see here we have trained data, especially there is a split, there is a normal data of 1341 and the pneumonia 3875. And similarly on the test folder, we have 234 normal images and pneumonia 390 images. And the validation, I don't want to tell the machine whether it is normal or pneumonia, but I just want to tell them we have an image, but you have to tell me whether this belongs to normal or pneumonia. This is how the challenging data set seems. So with that, we will be moving to our data augmentation. Have you heard about data augmentation? So very simple. Sometimes we may not be able to get a required number of data for every AI training model. So we need to train the data such a way that we are going to flip the data, we are going to zoom the data in and out, we are going to scale the data, all kind of augmentation, so that we will be having more and more number of images from the existing data. We are going to kind of upskilling. We are going to make more number of data from the existing data. The concept is called augmentation. In this case, we are going to rescale it. We are going to zoom and flip with 0.2 and horizontal flipping is equal to true. With that, I am going to generate what is my train data and what is my test data. You can see here I have 5216 images belong to two classes. One belong to normal and one belong to pneumonia. So next step is very important. You can understand this is actually the magic. So you can see I am going to take the images and I'm going to display it. So it's running now. Let us wait for that. So there are some images related to normal and there are some images related to pneumonia. So I am neither a doctor nor a radiologist, but I'm just a data specialist. I can comment anything on the result, but not on the textures. I'm very sorry. This is the beauty of AI. So some commands is given and I have some images of normal and I have some images of pneumonia. I wanted to explain something on two images from the above only, very simple, but I this time I want to generate only two images. One is for normal and one is for pneumonia. Here is the beauty. So how a AI model classifies just X-ray images? Basically, they will learn what is normal. Normal means a healthy chest X-ray looks like. In this typical image, the first one, the lung tissue has a consistent feature. Or we can say that I'm not a doctor, I'm not a radiologist. Major mistakes may come. I'm very sorry for that. So lung tissue has consistent texture, and the organs like the heart and lungs have well-defined shapes and boundaries. You can see almost it is clear and evident from the picture the organ has well-defined shapes and boundaries. How do AI come into the picture? The AI identifies the deviation from the normalcy. Very simple. It identifies what is there in the left and how it changes to the right. The right, I can see one sample of pneumonia X-ray. It's nothing but the deviation from normal state to detect pneumonia. It examines the texture of lung tissue and identifies irregularities that signal infection. I don't know whether it is bacteria or kind of a virus, but definitely there is a heterogeneous pattern seen in that image. AI focus on the shapes and identifies the alterations in the boundaries of organs like heart and lung, which can become distorted by infection. I hope this is clear. This is by an AI or data perspective. Furthermore, an AI model recognize pattern such as presence of infiltrates characteristics of bacterial or viral infection. From a radiology standpoint, the model highlights the area of increased abnormalities, which are crucial for diagnosis. For example, pneumonia presents in a distinct pattern, and then the AI model detects the deviation from the normal to infected states. I hope this is clear. We are moving to next, which is nothing but loading a pre-trained BGG model. Now we integrate VGG62 in VGG16 in our project so that you can see I am considering this as a VGG16 trained on ImageNet library. We have more than lakhs of images. So this is going to be our base model. We are loading VGG16 without its fully connected layers. You can see here the base model only we are taking from VGC16 next onwards our my own layer. So we have set trainable is equal to false, which nothing but freezing the pre-trained layer. I don't want anything from the top say that my output is based upon my own data, which preventing unnecessary modification. Again, we stack additional dense dropout, batch normalization layer, everything to specialize the model for pneumonia detection. So our final architecture include a VGG16 model, a fully connected dense layer with dropout, batch normalization, etc. to specialize the model for the pneumonia detection. I hope this is clear. Again, I'm going to run this model. Considering base model is a VGG16 run on image library, and I'm modifying the base model based upon my requirement because my data not belongs to one of the data from the ImageNet, but this is something different like a chest X-ray images to detect pneumonia present or not. I hope this is again clear. We are going to compile this model. What do you mean by compiling this model? We are going to defining what is my model, and I'm going to define what is my optimizer. Technically, my optimizer is something called Adam, and I'm going to define my computation. Maybe technical people can understand. I'm going to define binary cross entropy loss function. Since we have only two classes, nothing but normal and pneumonia classes. Hope this is again clear. I'm just going to compile it, model.compile. So we are up to here. Now we are going to fit the model or we are going to train the model, which is the very major and interesting steps. So we are going to train data, which is nothing the train data which we are passing each and every images of 3000 plus images, whether it is a normal or a pneumonia images. And we are going to validate on the test data whether once the training is over, they are going to take it and converting and testing on the validation data, and we will be using a test epoch of 5 epoch. You might be thinking this is very simple. This is the magic of deep learning. Depends upon data, depends upon the images. It may take time. So just executing it, you can see the execute started 1 out of 5. It may take at least 30 minutes to complete the training. So I'm stopping the recording now. Let's find where the I can see one epoch take minimum 5 minutes. So the recording is stopping in this case. We will be back after 30 or 40 minutes. Just and we are back after the training. It's almost how many minutes? 500, 500 also. 5 epoch consisting of minimum 500 seconds, almost around 5 into 500, 2500 less than an hour. This is what we call training. And you can imagine for a simple data like the which minimum around 3000 plus image, we got around 50 minutes. So imagine if the data is very high, the computation time is going to increase like anything. So with this, we just wanted to understand, we completed the training part, 5 epoch, and this can be increased. The epoch can be increased so that may be a better training accuracy. And also this part where we call it as a learning grid that can be changed. That is another fine tuning. And also if you want to change the loss function, we have given binary cross entropy that can be changed to some other thing. And if you want to report the performance, we have given accuracy that can also be changed to some other performance matrix. So we have done with this basic parameter, and with that we got almost 0.89 in the first epoch, and it reaches to 0.94 in the last or fifth epoch. The loss function changing from 0.31 to 0.15, which is basically this is decreasing and this is increasing. And the validation accuracy from the beginning it is 0.81 and increase to 0.83. This is a good sign. And the loss function, which is nothing but 0.41 and increase to 1.11, which is not a good sign. I can see here it is decrease, then again increase, then again increase. There are some problem with the data. Very simple. So this is the kind of interpretation we have to give in terms of model training. We can't say that which model will work better with what data. It's all about train and test, or we can say that in simple trial and error. So we have seen something called model. So what do you mean by model? I just want to spend 1 second time. What about model? Model is nothing but a mathematical representation of a program that learns from the data and make prediction or decisions. It does this by adjusting the internal value. So internal value, people will say that very simple. This is nothing but weight. That weight is going to adjust and which control the how the model respond to the input. So this is the importance of this kind of a neural network. And we are going to adjust the weight so that we are going to get a best model. Basically, the train happens in cycle as we call epoch. As I mentioned, we have given 5 epoch. This is nothing but cycles. In each and every epoch, the model processes the data and updates its weights using an optimizer. We have given an optimizer called Adam. If not Adam, you have some other called SGD, nothing but stochastic gradient descent. There are so many other optimizers are there. You can use anything. Again, that's again trial and error only. So a method that this particular optimizer we will call as a method that helps improve the performance. Basically, the optimal error is reducing error. So as we mentioned in the scikit-learn, whatever it is, our optimum aim is to reduce the error of the function, basically reducing the cost function. So we have and check everything. These errors are measured using loss function, which tells how the model prediction from the corrected answers. So our aim is to reduce the error or minimize the error over time. So we can say that time versus error has to be reduced. To monitor the progress, accuracy and training loss, which show how well the model current data. So I'm reducing this or I'm just clearing the all drawings. You can see in the next picture how the performance metric about this particular VGG16 model. It's all about monitoring the progress. As I mentioned, we use the training accuracy and we use the test accuracy, we use the validation accuracy, everything, and we are going to run it how the model accuracy and how the model loss is increasing or decreasing as per generic requirement. The accuracy has to be increased over epoch and the loss function has to be decreased as per epoch. So this is the normal norm. However, it's all depends upon data. However, depends upon all your fine tuning. So how well the model performs on new or unseen data, that's very important to ensure it's a truly learning or just memorizing the function. So I just wanted to conclude or I just wanted to understand how this particular model is behaving with the new data. I have given two data, which is like a subplot. I have given one data which is predicting as a normal and another one which is predicting as a normal. I can see the first one belong to pneumonia. Predict. I can see here something. What I can say, it's predicted normal and predicted normal. Another one we can see one more where I just wanted to show some interest. This is all about test data. So not anything from the unseen data. This is all from the test data which is running now. I can see there are two pictures. The actual is normal and the predictor is also normal. And the second one actually is normal and the predictor is normal. We have done the scripting like this. Very simple scripting using Python. And I wanted to load another few amount of data, maybe 5 to 10 with keeping a threshold of 0.5, whatever comes amount 0.5 has to decrease or increase. We can see that I'm giving all the pre-processing. So I just wanted to wait for how it's recognizing for a series of images. I can see the prediction pneumonia, pneumonia normal, both are there. And finally, called saving a model, whatever we trained in this upper or the above has to be saved like a model. As I mentioned in this particular step, where we are going to save this model, this is the model, and this is the compilation, this is the model training, and this is the epoch. In this particular, we are going to train this and we are going to save this model as in future we can reusable. That's very important. We are going to reuse this entire model as a pneumonia underscore bgg 16 underscore h15. We are going to retain this and we are going to use it. That's what it happened in the previous deployment stage, where we use this entire code for reusability purpose. So that's what how we can leverage bgg 16 and transfer learning. So we built a fantastic model.